So this is multigrid solvers in Trilinos, or multigrid solvers in MueLu. And I mean, we have a whole whole lot of them. And I'm also always getting confused about like which one is which. So I figured I'd just like try to.
Did you turn on the mic?
I totally didn't turn on the mic. It says on, and it says something on it. Okay. These are my overview sites in place of actual documentation to give some introduction to the multigrid solvers that we have in Trilinos. So let's see, what are we actually trying to achieve here? So let's say we have this curl system at the top. This is what we want to solve. There's some parameter mu on this mass term, and there could also be some parameters on the curl part of it. We'll have some boundary conditions to that, and one really good way of thinking about this sort of system is to embed it in the RAM complex that Mauro already had on his slides earlier, which is this exact sequence between the relevant spaces here. So hgrad, that's your usual like h1 space, and then an hcurl space, which you will typically then use some hnetter-like elements on, and so on. Okay, the same sort of exact sequence you'll, yes? Oh, so you sort of see this like mapping from one space into the next. And this means that the image of one mapping maps directly into the null space of the next mapping. And this is sort of like important properties that are sort of like encoded in the sequence. It's sort of like a pure mathy way of like encoding things that physicists have like known for like, well, hundreds of years. Okay. We have the same sequence, and we were sort of trying to like preserve the structure. So we have the same sequence also at the discretization level. So what I'm saying here, this is my H1 or hgrad space. We'll use our typical nodal finite elements for that, for the discretization of it. And then there's matching other spaces for hcurl and hdiff. So hcurl, these are typically at the lowest order edge-supported finite elements. So the degrees of freedom sit on the edges. And then for hdiff, we have phase-supported finite elements. And in what follows, I'll always talk about like nodes and edges and faces to sort of like talk about these different spaces. All right, so we have a discretization now of our curl plus mass system that looks something like this. So we have mass matrices sitting there, and then we have discrete differential operators flying around in there. Normally, if you just directly assemble everything, you might just like think of all of this as a stiffness matrix, but you can also write it as this triple product between a discrete differential operator and a mass matrix that's then like sitting on the next space over. So here we have our mass matrix on our edge space, and then we have a mass matrix on the phase space. Okay. And sort of like one of the key observations for the construction of effective preconditioners or solvers for this curl problem is that this operator here that looks quite different depending on whether you're on the null space of this operator here, of this curl operator, or if you are on the complement of that null space. So if you're on the null space, effectively this entire term here just disappears, and all you see in the action of the system matrix is the mass matrix. So great, that looks like a mass matrix. On the other hand, if you're not in the null space, then you get this second order differential operator. Now you might say, well, okay, I mean, the structure looks fairly similar also in the nodal case. I mean, you could imagine that this is the nodal mass matrix, and this is the edge mass matrix, and then this is just like your usual Laplacian operator. Why don't they have the same problem there? And the difference is that the null space of your usual Laplacian, that's really quite tiny. It's exactly like one vector, the constant one. Whereas here, every single gradient is in the null space of that operator. And so what that means for us is that we really need to precondition on two different spaces. We need to precondition one on the space where this is actually active, this second order differential operator. And we then also need to like precondition on a second space that is related to the null space of that operator. And the matrix that is associated with that is this sort of a projection of our system matrix onto that null space. And that is just a Laplacian matrix. So that's essentially the main idea of preconditioning for Maxwell problems. All right, so I've talked a little bit about these discrete differential operators. So what do they actually look like? The first guy is the discrete gradient operator. And there's an operator that essentially moves between a nodal discretization and an edge discretization. It's a gradient. OK, so this can be cast really as a signed incidence matrix, which connects the nodes in our mesh with the edges where the degrees of freedom for our edge discretization are sitting. And it sort of assigns weights 1 and -1 to each edge, which then corresponds to sort of the orientation of that edge. Similarly, you can write down your discrete curl operator, but this is a signed incidence operator that connects edges to faces. Now, this is a 2D picture. You can imagine the same thing happening in 3D as well, but it effectively connects your edges to the faces that have these edges as its boundary. And again, the signs essentially correspond to how these edges are oriented so that sort of like form a nice loop. So you can see, OK, positive side, a positive sign, and then a negative sign because we want to actually close the edge there, the face. All right, so in practical terms, you don't really want to worry about this, but you need to somehow, if you want to use these solvers, you need to assemble these guys. And there is a really neat little trick. So if you have your finite element code, then you can just assemble them via a combination of taking gradient and then interpolating that into the correct space. So you can totally get that operator with sort of regular assembly techniques that you already have, or most likely all you have. If you're in Trilinos, you can get that with a combination of Panzer and Interpret2. And we also have this in for higher order discretizations, where these operators look quite a bit more complicated, and you can get this sort of in matrix-based or matrix-free mode. All right, so we've identified these two subspaces on which we need to solve on this edge problem and a nodal problem that is sort of the projected edge problem. And so the simplest sort of iteration that we can run on this is a so-called hybrid or Hipmeyer smoothing. And really all it does, it sort of alternates between smoothing on the edge problem, so your original Colcord problem, and then the problem projected to the nodal basis. And so the operator that you need to use to switch between back and forth between the two of them is this discrete gradient operator. If you want to use MueLu, which is the multigrid in Trilinos, then these are sort of the parameters that you have to set. And it's really just saying, OK, you want to use a Hipmeyer type smoother, and then you can set the two subtypes for the edge problem and for the nodal problem. And unfortunately, we're sort of mapping a little bit between type 1 and type 2, and you have to know that type 1 is the edge problem and type 2 is the nodal problem. All right, so obviously, we don't want to just use a smoother. We want to actually use algebraic multigrid for all of this. But let's take a step back and just think, how can we use geometric multigrid to even make this work? And what are the steps involved to make this work? So we have our two subproblems, a edge problem and a nodal problem. So we'll construct two multigrid hierarchies for this. And what we will do then is we'll try to sort of match them up nicely, and then at each level, we will simply use this hybrid smoothing idea and combine the matrix from our edge problem with the matrix from our nodal problem. And that's all it takes to solve call equations with a geometric multigrid. And this idea, obviously, if you want to use something like a higher order discretization, you can directly use this idea and use it as a peel multigrid, where you essentially coarsen on the finite element discretization order. So this works all the way down to first order, and at that point you need to figure out how do you actually want to solve that problem. That's where we come in. So okay, so let's say we have our we are considering lowest order finite elements, and we have formed our nodal problem with this relationship that I showed before by essentially projecting the edge problem. And let's say, for argument's sake, that we have somehow magically constructed prolongation operators that we need in multigrid, both for our nodal problem and for our edge problem. So with these superscripts for n for the nodal problem and e for the edge problem. Well, then we clearly want to have the same relationship be satisfied again, because we want to like sort of recurse on all of this on the course level as well. So same relationship as above. We also want to have that on our causal level. And so in order for this to be satisfied, really what this boils down to is that we need to preserve this commuting relationship that links together the edge prolongator and the nodal prolongator via these discrete gradient operators on both fine and coarse level. And so this is really our main job now. If we want to do algebraic multigrid for curl problems, this is sort of, I mean, we clearly know how to coarsen a nodal problem, but we need to make sure that for our edge problem, we preserve this commuting relationship. This is like our main goal. All right, so let's say that, I mean, we know how to coarsen nodal problems, so let's do that. We have taken our nodal matrix and we coarsened it, meaning we have constructed a nodal transfer operator to a coarser mesh. So in my picture on the right here, we have sort of like our very simple mesh, and we have decided we are using plane aggregation for this. So we have essentially like just formed 3 aggregates. These are our 3 unknowns for the nodal problem on the coarse mesh. So we sort of like reduce the size of the problem. Okay, so now the question is, well, how are we connecting these 3 unknowns in these sort of like blue blobs? How do we connect them together with edges to form a discrete gradient operator on the coarse mesh? And I mean, the simple idea is, okay, I mean, if 2 of these blue aggregates, if they possess nodes in them that were connected before with an edge, then they should still be connected after this coarsening step via an edge. And in this particular case, well, yeah, we're just connecting all our 3 aggregates together. So that's the construction of our coarse discrete gradient operator. Again, I mean, we remember this is just a signed incidence matrix between our coarse nodes. Okay. The second step of then constructing an edge prolongator that effectively satisfies this commuting relationship, that's a bit more algebraic, and I'm not going to show this here, but it's relatively straightforward. So all of this is already quite a bit old. So from 2002, it's called the Reitzinger-Schöbel approach, and it effectively allows you to construct an algebraic multigrid for Kirk-Hall problems. The only problem with it is that the preconditioner generally isn't scalable. So we don't really want to use that in practice. All right. Fortunately, a couple of people had a good idea how to improve on this preconditioner, and this reuses a sort of a classical idea of how do you improve a sort of like slightly cruddy prolongator, and that is by applying a smoothing operation to it. So we're simply applying sort of like the matrix variant of Jacobi to this to our candidate, to this guy that we just constructed using this Reitzinger-Schöbel approach, and in that way improve its quality by effectively dampening out certain or reducing the energy that this guy essentially carries. Now, we need to remember that we sort of still want to like preserve our commuting relationship between our 2 hierarchies, between the edge hierarchy and the nodal hierarchy. So we cannot decouple this step entirely between the 2 hierarchies. So we sort of need to mirror this with a second smoothing step on the edge operator as well. And then there's also a third smoothing step that we can take that is sort of like independent of the nodal hierarchy, that only applies to the edge hierarchy. Now, one thing that I sort of want to stress here is that these smoothing steps, they improve the quality of the resulting multigrid, but at the same time, they also increase the density of the prolongation operators. And what that means is that overall, this will be a more costly multigrid hierarchy. So if we're now doing things like applying 2 smoothing steps to the same sort of operator, then this will have quite a significant density. And because we also do this like on every single level to construct our transfer operators, this will sort of propagate through the entire hierarchy and create a really, really dense hierarchy towards the bottom at the causal levels. Again, I'm showing the the relevant parameters for setting this up with MueLu, and this should be sort of it maps between like what I'm showing up top and down here. You're sort of bound to using a smooth aggregation multigrid for the nodal hierarchy, and then the matching smooth right-Singer-Schobel approach for the edge hierarchy. All right, so now this is our sort of new approach, which tries to handle some of the drawbacks that the previous methods had. So we want to decrease the energy that is sort of associated with this prolongation operator, and instead of like trying to explicitly do this by applying a smoothing operation, instead we try to enforce that by solving an optimization problem. Essentially, we're saying, let's try to find the optimal prolongation operator with the minimal energy. Subject to two constraints. One, we still want our commuting relationship to be satisfied. So that's a sparse constraint. These are all matrices. And then the second constraint is that we want to effectively fix the sparsity pattern of the prolongation operator up front. And this gives us all the control that we want about how much density do we allow ourselves in our multigrid hierarchy. Okay. Let's see. In practice, solving this optimization problem for us typically means doing 2 or maybe 3 steps of projected CG. So this is definitely not a solution, but it typically gives us the most bang for our buck for the first couple of iterations, where sort of like the loss function goes down quite significantly, and after that it sort of like slows down. We're not getting as much out of it anymore. I should also say that the solution of this involves the inversion of a large block diagonal system, with the blocks typically being like on the size of, I don't know, like 10 to 20. So what we're using for that is Cocos kernels batched LU. We also have some option for using Belos for that directly, with some sort of like small modifications to make that work. And we would ideally want to switch to a batched QR also from Cocos kernels. And what I want to stress at this point is that this fully decouples the nodal hierarchy from the edge hierarchy. So now we can use all the different good multigrid algorithms that we would want to use for the nodal hierarchy. We can essentially pick whatever the best option is in our particular case, and then match it with energy minimization for the edge hierarchy. Then what I should also mention here is this is the linear solver that Roger showed earlier as what is used by Empire, and that follows a slightly different idea. And I'm only showing one slide on that. But that is, okay, we're back to our PDE. We want to solve curl plus some mass term. And what we will do instead is we'll try to sort of like jam something into this null space that is giving us so much trouble. So we'll augment the curl part with a grad diff term to effectively form a vector Laplacian operator directly. And when we then, I mean, in the next step, we have to like pay for this sin that we just committed, and that effectively gives rise to this 2x2 block system, where we sort of rediscover essentially the same players as before. Again, we will have our edge problem and our nodal problem pop up, but what we'll do this time instead is that we will use a block Jacobi preconditioner to solve this, and we'll use AMG directly on these 2 subblocks, because now with this augmentation here, that's a vector Laplacian, and multigrid in itself should already be a lot more easy to just directly apply to something like that instead of the curl part only. One further thing I want to mention here is, because we're using a block Jacobi preconditioner for this, and using multigrid for each of the diagonal blocks, we can effectively, on coarser levels, where we're sort of like running out of work anyway, we're rebalancing. That means that we're sort of contracting the communicator on which we're running this. And that means, oh, we now have to solve 2 hierarchies. We can just do this at the same time in an additive fashion. And so this might not always give, this preconditioner might not always give a very low iteration count, but the iterations are really, really efficient, because we're sort of reusing our communicator on the coarser levels quite efficiently. And I should also say that this time there's no preservation of this commuting relationship that I said earlier was so important. So there's some drawbacks. All right, so I've sort of like gone through a whole lot of different linear solvers that we have available for curl. So it's now time to put them to the test. So this is my numerical experiment that I'm doing to sort of like tease out some of the differences between these solvers. So this is the simplest and silliest possible example for a curl problem. We're solving curl on a box. We sort of like the difficulty of the problem will be judged by this CFL number, which effectively links the mesh size h to the size of this coefficient in our mass term. And we'll consider two different use cases. The one case where we essentially fix the coefficient of our mass term and just do a mesh refinement. And then the second case where we link the size of the coefficient with our mesh size, and this sort of like mirrors more closely what you would see in a time stepping example. And we'll look at a lot of different solver combinations. So the first one is this Reitzinger-Schöbel Maxwell 1 type preconditioner. Then we'll look at the smooth variants of that, where we sort of like vary over which prolongators get smoothed, like nodes or edges or both. We'll then look at these new energy minimization multigrids. We look at two cases here. One is sort of like the way it's intended to be used with two optimization steps to improve the prolongator. And then in a second case, we'll just look at what happens if we entirely skip the optimization and do no optimization at all. And this is sort of interesting because you might think this should actually perform absolutely terribly, but it actually does reasonably well. And we're still trying to understand why exactly that is.
Question?
Yes?
How is that different than just doing Reitzinger-Schöbel?
Right. So it is different because you effectively have to somehow... Reitzinger-Schöbel is fully tied to like a piecewise constant nodal prolongator, whereas this is not. We have a mechanism to effectively construct our initial guess for the optimization that satisfies the commuting relationship independent of the fact that the prolongator is piecewise constant. Okay, the last two are then these, sort of what I showed on the last slide, these two ref maximal type preconditioners. One where we don't do any smoothing at all, so that's plain aggregation, and then one where we use smooth aggregation. And all of this is done on a Broadwell system at Sandia, and the caveat here is that these are a lot of different solvers. I'm sure there's optimization potential for many of them, but I try to keep it as fair as possible, reusing a lot of the same settings between them. All right, I'll try to step through some of the results. So this is for hexahedral elements, and this is a weak scaling study. And in each of these little boxes, I'm recording the number of iterations, the solve time, and the setup time. So the first observation is that these unsmoothed variants that we have, so Maxwell 1 Reitzinger-Schöbel, and the unsmoothed ref Maxwell, the one that I highlight, they're not scalable. Okay, we can sort of exclude them already from our consideration pretty quickly. The second observation is that if we do this Maxwell 1 type preconditioner with all the smoothing enabled, so with sort of like double smoothing on the prolongators, that builds extremely dense matrices and ends up running out of memory. So that's not great. Now you might say, okay, if we don't do all the smoothing, but only some of the prolongator smoothing, do we still get good iteration counts? Because, I mean, on the left column with alpha and beta smoothing enabled, we get really great iteration counts, but, well, it's just way too dense. And the observation is that no, these two smoothing steps really are required for this particular problem. And yeah, the matrices still get fairly dense even if we don't do all the smoothing, and we still have relatively large setup times. So that's not great. The smooth variants generally seem to scale pretty well. So we get iteration counts that more or less scale with the logarithm of the CFL number. So that's pretty good. The difference in setup time between like the the no optimization part of the new Maxwell 1 algorithm and the actual optimized one effectively tells you the cost of doing the optimization. And that's currently still pretty significant. And that's because it's relatively new code. We haven't fully optimized that yet. We think we can still improve that quite a bit. But overall, we're pretty happy with the iteration counts for these new methods and also the solve times. Let's see. Generally, this is sort of like what I mentioned earlier. The ref Maxwell iterations tend to be, I mean, we need to take more iterations for ref Maxwell, but they tend to be faster. And that's the effect of sort of like overlapping these two hierarchies at the coarser levels. We can do the same with TETs instead of hexes, so we get sort of like denser matrices to begin with. And the new algorithm, the energy minimization algorithm, seems to be doing a little bit worse on these types of meshes. But we're hoping that by sort of adjusting the way that we're doing sort of like dropping on our different levels, we can actually regain some of that performance. But so far we haven't. So this is a snapshot of what it is right now. OK, so this was all with for the case where the CFL effectively grows over this weak scaling study. If we fix the CFL, then we see that, well, it doesn't really, I mean, all these scale absolutely perfectly. And at this point, the sort of choice of what you might want to pick, so if you're time stepping through a problem, might look a little bit different from when you're solving essentially the steady state cold core problem. All right, so to conclude here, I think there's really only very few sort of like problem quantities that you want to look at when you like pick the solver for your problem. The first is, what CFL regime are you in? Are you sort of like in this time stepping problem that Empire, for example, is in? Or are you actually trying to solve a steady state problem? Or are you at really high CFL already? And what is your ratio between the number of setups that you need to do for your preconditioner versus the number of solves? This is really the main two parameters that determine which solver you should pick. Problem size obviously also comes into the play, but I'm not sure if you necessarily want to tie your solver choice to problem size. I think I've shown you that this new energy minimization preconditioner seems to work pretty well. There's still a lot of room for improvement, especially in setup, which is sort of specific to this preconditioner. Obviously, I've not shown any sort of actual interesting problems. I mean, there's no like variations in coefficients or boundary conditions, or I've not shown any GPU results here. I'm hoping to just sort of like tell a story that, yes, this shows enough promise that we want to keep on pushing on this, and also provide this on different platforms and try it out a little bit more. We sort of two topics that are more researchy that we want to look into is, I mean, we've seen for these ref Maxwell type preconditioners that this additive type way of applying the preconditioner really gives us fast iterations. And so we think we can sort of like backport that into this other family of Maxwell preconditioners. It might degrade the iteration counts, but it will also speed up the individual iterations. So that's something to try out. The other observation is this ref Maxwell type idea has been extended to the entire DRAM complex. So currently we're sort of really focused on the H-curl space. You can also apply this at other sort of spots in this DRAM sequence. We can do the same thing with Maxwell 1. And effectively what this means is that this is sort of an algebraic way of coarsening the entire mesh and creating actual coarse meshes in an algebraic multigrid approach. And this seems from an intellectual standpoint sort of interesting, and we sort of want to keep on pulling on this a little bit further. Hopefully something good comes out of it. So thank you, and I'll take questions.
Go ahead. Have you tried this on any messy material problems?
I've not tried it on any messy material problems.
Okay, let's fix that.
Yes.
No, we've been running long. Any other questions before we move into open discussion? If not, thanks.